Hi everyone. Okay, this is our last talk for the afternoon, I believe. And it's on Ristretto, runtimes for JavaScript. We have Shane Stevens presenting this, and Shane is a software engineer at Google and a member of the Chrome team working on WebKit's implementation of CSS. He has previously been involved in other Floss-related projects, including libbogplay, I think I said that right, which is a library for synchronized playback of OGG media, the Anidex Fireflux plugin, and the Google Wave project as part of the API team. So welcome, Shane. We're looking forward to your talk.
Thank you. So yes, I am a Googler working on Chrome, specifically on CSS and web animations. But actually, I've also got to admit that I have an unhealthy interest in type systems and in type theory. So I'm actually here to talk to you about an idea in that area called type contracts and an implementation of that idea in a library which is called Ristretto. I also need to apologise. I seem to have come down with a cold just this morning, so if I'm croaky or have to sneeze, I really do apologise. So a very quick introduction of the area is that type contracts are a way of providing things that look very much like static type signatures in a dynamic language, but without having to modify that language at all. And Ristretto is an implementation of type contracts for JavaScript. And I really need to thank Phil Wadler, who came up with the type contracts approach, and Sam Lee, who, as an intern at Google for the Chrome team, built a large part of the Ristretto library. Right, so an outline of this talk is that I'm first going to talk about the great debate between static and dynamic type systems, and how that debate motivates the idea of type contracts. Then I'm going to introduce what type contracts are in more detail and show off some of their features using Ristretto. Then I'm going to try and give you sort of a feel for how Ristretto works in the real world. I can't do a full real world demo because we just don't have enough time, but we'll do a little cut down one. And after that, I'll get into some of the details of how type contracts work, just a quick overview, at least how they work in Ristretto, and then I'll talk about some ideas for further extension of the idea. Right, so most of you have probably already chosen sides in the question of whether to program in a statically typed language like Haskell on the left, or a dynamically typed language like Python on the right. Even if you haven't chosen sides, you've almost certainly been involved in part of at least one heated argument about over which approach is better. So just so that we're all on the same page, a statically typed language is one that requires all of its things, variables, expressions, classes, functions, all that sort of stuff, to have an unchangeable type, which is knowable at compile time. On the other hand, a dynamically typed language operates under the assumption that programmers, they pretty much know what they're doing, and it tries to let people do pretty much anything to pretty much anything. So the type is mutable over the course of the program, of everything, or of many of the things. So I mean, based on these descriptions, it's pretty clear, right, that the dynamic approach is, hang on. Right, so based on these descriptions, it's pretty clear that the static approach is correct. And look, there's benefits to both approaches, and I actually want to go through some of the benefits and drawbacks that the two approaches provide. So advocates point to duck typing and similar things as one of the major advantages of a dynamically typed system. Duck typing is basically the ability to use any object in any scenario as long as it has the right interface. You know, people say if it quacks like a duck, then you can treat it like a duck. So this provides a lot of flexibility. It means that, that objects aren't required to declare their abilities up front. In fact, objects from one module can be used in another module without either module knowing about the other one's existence. You just need to have a little bit of repurposing going on in the middle. Okay, so that's one of the major benefits of a dynamic type system. Dynamic language programmers also claim that their languages allow for faster implementation and faster refactoring because small changes in responsibility don't fan out all the way through the types in the system. And they claim that their languages are easier to learn because neophytes aren't burdened with learning a potentially complex type system at the same time as they're learning the language. Right, so all of these advantages point to a picture of flexibility or tolerance as the basic advantage behind dynamic typing. On the other hand, the advocates of static type systems and static languages point out that the type systems in these languages allow for early elimination of a whole range of errors that would otherwise need to be tested for. They also claim that statically typed compilers produce faster programs, and that type information is actually a form of self-generated documentation. Not only self-generated documentation, but documentation which is always consistent with the code. And this points to static languages being all about, structure, rigor, high information content, giving the compiler more to work with. So the debate between static typing and dynamic typing, as exemplified here by Haskell and Python, can be recast into a debate between structure and flexibility. Do we give the computer extra information about what we're trying to do and let it help us find bugs and go fast? And accept that in order to do so that we have to restrict ourselves to obeying the rules and regulations of whatever type system the language provides? Or instead do we strive for generality, for the ability to program pretty much in any way we see fit, and accept that this means we're on our own as far as correctness is concerned? And when you think about it, any individual argument between static type system programmers and dynamic type system programmers basically comes down to this, to structure versus flexibility. Testing, for example, dynamic advocates will say, we're much better at unit tests. We can write more unit tests because you can be much more invasive and you have more access into the objects and blah, 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 blah. Static programmer will turn around and say, well, yeah, but wait a minute, we don't need to write as many unit tests because we've already given all this information. We've got much more structure that we've given to the compiler. Okay, so structure versus flexibility. What if we could use both of these approaches? So it turns out, at least to a certain extent, that we can, and that the idea which lets us do this has actually been around for quite a long time. The idea is contracts. The contracts date back at least as far as the ARFL programming language. That was invented by Bertrand Meyer in 1986. And contracts are just programmer-specified properties of code. Like type information, they provide information and documentation about expectations and guarantees of functions and invariants of data types. For example, a contract might indicate that the input to a function must never be negative, or that a function will always provide a sorted output, or even that a tree data type will always have more nodes on the right-hand side than on the left-hand side. However, unlike type information, contracts are generally checked at runtime, and they're often only checked during development. And so the idea of contracts provides a number of advantages and disadvantages. On the advantages side, type system complexity is generally limited by the ability of the developers of a language to build efficient type solvers. Without an efficient type solver, compilation would be just too expensive. But on the other hand, contracts only make point checks on data, and therefore they can enforce fairly complicated requirements without that complication encompassing the whole program. So contracts can be a lot more complex than type checks can be. Type systems also lay out the shape of a programming language. Haskell, for example, feels very different to C, and this is partly because the Haskell type system requires everything to be side effect free, and also permits partial application of functions. So these are two features of the type system that really impose the way that a programmer uses Haskell. Contracts, on the other hand, are completely optional. You can use them, not at all, partly, or completely in an application. And they can be built on top of rather than into a programming language, right? So contracts don't impose on language design. And in fact, multiple contract systems can happily coexist inside a single programming environment, and they can even have completely incompatible assumptions about what it means to be an object or a function. Okay, so contract systems could be internally inconsistent, which doesn't sound like an advantage, but actually it is. It means that you can use different approaches in different parts of your application as you see fit. So actually, contracts really do feel like just the dynamic programmer's way of importing some of the benefits of a static type system. Hey, we'll have that type system, but we're going to make it more flexible, right? On the other hand, this approach does come with some disadvantages too. So first of all, contracts, unlike types, can't actually prove anything. They operate strictly at the place they're inserted, and they can only inspect values which are actually provided. Contracts can't be used easily, at least, for whole program information. You can't, for example, track the amount of memory used or the number of threads running, because you need to wrap every single place where memory is used, or every single place where you start a new thread in order to track that effectively. And contracts can be quite expensive. For example, checking that a tree structure is balanced is going to be order n on the size of the tree. And this is generally why contracts don't get used in deployment, that they only get used while you're developing an application. And finally, contracts can be awfully verbose. So when you look at this, these first 2 points are pretty much straightforward extensions of working in a dynamic type environment anyway. Like, if you're working with a dynamic type system, you already can't prove anything, and it's already very hard to look at any kind of whole program properties. The third is mitigated, as I mentioned, by just switching contracts off in deployment. And the fourth is pretty much unavoidable. I mean, we're adding information to the code. You have to be somewhat verbose if you're providing more information. But it can be minimized, and type contracts are actually a way of doing that. So let's have a look at what type contracts actually are. On this slide, up the top here we have an Eiffel contract. This is what contracts look like in Eiffel. This is talking about an implementation of a bank account object. And to understand what it says, you really need to understand details about that object, lots of details about that object. I mean, it's relying on all deposits, on balance, on this total method, which is on all deposits. If you don't know what these things are, then you don't really know what this contract is saying, okay? It's also very verbose. In general, it's just quite hard to read, quite hard to understand. A type contract, on the other hand, is a contract that looks just like a type signature. So here's one which looks like a Haskell type signature that says, you know, this method, do that thing. It takes an int, and then it takes another int, but yeah, that might be undefined, and it takes a method that converts strings to foos, and it returns bars. So it's much cleaner, much easier to understand. Generally, type contracts provide information which is more relevant at a glance. All right, so Ristretto. Ristretto is a type contract library for JavaScript. It's implemented entirely in JavaScript. It runs in the browser. It runs in Node. When I say it runs in the browser, I've only tested it in Chrome. Might run in Firefox. It includes a parser for Haskell-style types. It supports a wide variety of basic and advanced functions, which we'll go through in a minute. And not on this slide, but very, very important, is it's just a prototype. It's not at all ready for use in development. It's a proof of concept where we're trying to see if this approach works. So why would you go with this approach of runtime type contracts in a library that sits in the browser? There are actually some other approaches around. One example is the language Dart. The Dart is a whole new language intended for browser development, and it has optional types. It effectively has type contracts built into the language. Okay, so why would you go with something like Ristretto instead of Dart? Dart requires you to change the way you write code. Okay, it's a big change. You have to switch to a new language. It's not at all clear that it's going to be widespread in the future. And furthermore, because the type contracts are built into Dart, they don't change. You get the set which the developers of Dart provided for you. So Ristretto is a lot easier to adopt and a lot more flexible in terms of what it can give you. Why would you use Ristretto instead of something like JS Compiler? JS Compiler is a backend that you can use, again, to provide type information in JavaScript, which is checked statically before the JavaScript is minified, and then sent to the browser. Well, one of the problems with JS Compiler is that it often has to punt on proving a property about the code, because JavaScript is just too flexible, too dynamic to do any sort of meaningful static type checking on. Okay, so it's more of a static check, whereas Ristretto is more of a dynamic check, and as a dynamic check, it fits better with the way that JavaScript works. Right, so what I'd like to do now is take you through some of the features of Ristretto, show you basically how to use it, and then we'll move on to a real-world example. So here we have a very, very simple use of Ristretto. We pull in the Ristretto library. We grab T, which is the basic function you use for providing type information. And then we take this function here, function a, b, return a plus b. Okay, this is a function that adds two things together. And we wrap this function in a type signature. Okay, so by calling t and providing it with a type signature, what we're doing is we're getting back another function, which we're putting in this var add, that we can then use as a function, right? But before the function is called, the types of the inputs are going to be checked, that they're both integers. And after the function returns, the type of the result is also going to be checked. Does that make sense? Yeah, good. So if we call add with 4 and 5.0, with 4 and the string 5, with false and 5, and with 4 and 5.5, how many of these are going to succeed? Who thinks none? Anyone think 1? Yeah, but you already know. It is in fact 1. JavaScript doesn't distinguish between numbers which are integers and numbers which are not integers. All we can do is check the immediate value that comes through and say, yeah, that's an int. You know, if I round this, it comes out at the same thing. It's an int. Okay, so this works, and these fail. And when these fail, you get a type error. So this says, in add, I expected a value of type int, but you gave me this string thing instead as the second parameter. You know, here, I expected an int, but you gave me false in that first parameter. And I expected an int, but you gave me a number that I couldn't use as an int. Fairly easy to use. I should say at this point as well that it's completely optional if you include Ristretto to use it on any or all of your functions. You can just take 3 or 4 of the critical ones and wrap them. You don't need to put it in everywhere. It's very tolerant of having some functions marked up with types and others not. So it's pretty non-invasive in terms of grabbing it and just starting to apply it to your code. Right, so what are some of the features? We support the basic types of int, num, string, and bool, which are fairly obvious, I think. We also support unit and 0. Unit says basically this function should only ever return undefined. Okay, so this is a valid use of an int to unit wrapping. This says that the function a will take an int and it won't return anything. And 0 says that the function won't have any input. So this function, no input from 0 to int, doesn't take anything and returns an int. Okay, so that's your typical getter and setter. Setter and getter. Yes, setter and getter. We also support... Yep.
Why 0 there?
The question was why 0 there? And the answer is we had to have something. We were kind of stealing the type specifications from Haskell. Haskell doesn't have any concept of a function call that doesn't take any inputs because everything's lazy in Haskell, right? So a function call that doesn't take any inputs in Haskell is just a value. So we had to have something. We decided to use 0 because there weren't any inputs.
So camel would have actually said unit there.
And the follow-up was that a camel would have used unit there. I think we played around with doing that and it didn't work very well. But maybe we could make it work, I'm not sure.
Could you have called it something else, like empty?
Sylvia asks if we could have called it something else like empty. Yeah, sure, we could have. Like I said, this is just a prototype, so there's lots of scope. And the other thing about, the whole point of runtime type contracts is that if you don't like these, go and write your own. In fact, you can, like this stuff here, there's this little parser that runs that pulls all these values out and turns them into the contract objects, which are then applied. Right, so you don't even need to go and write all the contracts again. You can just write your own parser and use that. Right, it's very, very simple. We have nullable. What nullable says is whatever the type was that we're going to make nullable, it can now be that type or undefined. So here, this takes a nullable string and doesn't return anything. So the function, if there's a name, then say hello. Otherwise, say fine, then be anonymous. Okay, is an example of usage of nullable. We support functions. And a point I'd like to make here is when contracts the idea first sort of came into mainstream usage and was put into Eiffel and became popular, that was pretty much about the same time that the idea of functional languages and higher order functional programming was just starting to come into vogue. So I think Eiffel was released in 1986, Miranda was released in 1985, I think it was, and there was a proliferation of functional languages between 85 and 90, and then Haskell was released as a standard in 1990, and functional languages really only sort of took off and became popular after that point. Okay, so back when contracts were being introduced, people didn't really understand just how much you could do with type systems. And so they went the way of other procedural idioms and tried to give you procedural contracts that looked like normal code. But this is just the tip of the iceberg, and we'll look at some more complicated examples later of some of the power that you can introduce into a language if you do use types as your idiom for providing contracts. This here, this says take an int and a function that converts ints to strings and return a string. Okay, and the interesting thing about this is that that Ristretto will check for you that the first input is an int. It won't do anything with the second input until you try and call it as a function. When you call it as a function, it will check for you that the thing you give it is an int. And then it'll check that the thing that it returns is a string, right? And then when you return from this function, again, it will check that the output of that is a string. So you can actually, you can put some quite sophisticated information about the parameters that you're providing to a function or an object, as we'll see in a minute, and be ensured that those are checked. But furthermore, those won't be checked until they can be checked, okay? And it all just sort of operates under the hood. So object support at the moment is pretty primitive. We have like objects as records. This person object has a value, age, which is an int, and name, which is a string. Yep.
In that first example, if the fun pass to the function pass to do it itself has a contract, will it check that its contract is int to string?
The question was that in the first example of functions, if the function provided also had a contract, would it check that the two contracts match? The answer is no, it won't check that the two contracts will match, but it will attempt to apply both the contracts. So this is a pretty simple example, but in more complicated examples, you can have two contracts that don't look anything like each other, which will both apply to particular inputs and outputs, and they'll both be checked. So coming back to objects, they're a record with fields. You can extend objects to create other objects. So this is a type def of an employee object, which is everything in a person plus a field that says whether the employee is current, and a method fire that doesn't take any inputs and doesn't return any outputs. And here is an implementation that would match that contract. When you wrap an object in a contract, you get the checking forever. You're never able to assign an incompatible value to any field of that object.
Question, is the U like a union, or what's the...
question is, on the syntax, is the U like a union? And the answer is yeah. It's basically take everything on the two sides and combine them together. I'm not sure what happens if you try and provide the same field on both sides. Probably we just crash. Okay, more types. We support lists. Lists in Ristretto are homogeneous, so you can't have lists of multiple different types. This list is restricted to only contain numbers. We support dictionaries, which are basically objects, which are also homogeneous. In JavaScript, dictionaries are implemented by objects, and the keys can only be strings, so we don't bother making you specify the key type. It can only be string anyway. Now these are really restrictive, right? Like lists in JavaScript, you can use lists for all sorts of purposes. You throw, an int, a string, and a bool in there, and then you pass them around and you use them as low-cost objects. You can't do that here because your lists have to be homogeneous. But that's fine. Just don't do that, right? Just don't use. You don't need to use these contracts if what you're trying to do doesn't match what we provide. Or alternatively, write a contract which does provide that kind of check. This is a distinctly different field from what happens in a statically typed language, where basically the type system requires that you only use the objects which are available in the type system. Okay, I want to move on to some of the more advanced things that we do with Ristretto. Again, this is all experimental. I don't know whether you really do want to do this in JavaScript. We just thought, hey, maybe we can, let's try it. So the first thing we support is currying. Normally with JavaScript, if you have a function, and you say this function has 3 inputs, and somebody calls with 1 input, well, the function goes through and the other 2 inputs are just undefined, right? If the function says it has 3 inputs and you call it with 4 inputs, the call goes through. The first 3 inputs get provided to the first 3 parameters, and everything else gets provided in an arguments object. If you wrap your function in a Ristretto function type signature, we provide quite different behavior. In this particular case, we have a function that has 3 inputs. It's a linear transform, a really simple sort of linear transform, right? You take an offset from 0, a gradient, and then an input. You multiply the input by the gradient, add the offset, and return the result. Okay, but if you call that function with only 2 arguments instead of 3, what you get back is another function. Right? And that function only takes 1 input, and it's basically, once you call that function, you get the result as if you'd called it with 32, 905, and the last input. This is called currying. It's pretty common in functional programming languages.
If instead this was a bug and I had just forgotten to specify the last argument, I would have expected to get back an integer or number. Instead I'm getting back a function because I'm using this currying feature. Is there a way for me to declare at that line, hey, by the way, I'm expecting the return type to be a number?
The question is, if this was just a bug and I forgot to add the 3rd parameter and I really want to know about that, can I? If say you return this into something else that uses another type contract that expects an integer, you'll know about it because it'll say, hey, I expected an int, but I got this weird function thing. So if you really care, what you can do is you can put a type declaration here. You can say Celsius to Fahrenheit equals T, open bracket, int, comma, that value, close bracket.
Right,
and that'll tell you straight away, right? So here you see an example of calling these partially applied functions in practice, and that's currying, right? And it's kind of cool that you can do this in JavaScript, under the hood, as it were. Another advanced feature that we supported, because hey, why not, is type variables. This says, take a list of something, I don't care what it is, but they all have to be the same thing. Take a function that takes those things, whatever they are, and returns something else. And this function is going to return a list of those something else's. Okay, so it's polymorphic on the type. Because this is just a map for anyone who's familiar with the map function, right? Map a function across a list, okay, but with homogeneous lists. The interesting thing about this in Ristretto is that when you write a type function like this, the values which are provided, where you say, I don't care what the type is, actually get locked away cryptographically inside an object. And the only things that can unlock them are things which take that particular type. So while you can't prove that based on this type signature, any function that passes does map, you can prove that the only things that happen is that values are taken from that list, passed through that function, and put in that list. There's no other way to do anything with values on the input list. You can't, for example, generate new values and put them in the input list. You could, of course, delete values from the input list. And you can't generate any values of B except through that function. So it's kind of interesting that we can do that level of checking dynamically and at runtime. How are we going for time? About 20 minutes, is that right? 10 minutes, okay. Algebraic data types are another example. Algebraic data types are an idea that I encountered in Haskell at least. I think they're probably from there or Miranda or something like that.
ML.
From ML, right, there you go. Quite an old idea.
1970.
They basically say, rather than providing an object with a constructor and then you say, well, this object could actually be one of 2 or 3 different things, so I'll make it take a type field and then based on what the type is, I'll have different constructors and blah, 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 blah. They give you a much more succinct way of doing this sort of thing. So we're declaring a tree here. And a tree, right, it either has nodes, which have 2 other trees hanging off them. This is a binary tree. Or it has leaves, which have an int, right? In this particular case, it's a binary tree of ints. Or they're empty. They're just leaf nodes which don't have any value associated with them, right? So that's what this says. A B tree is either empty, or it's a leaf with an integer value, or it's a node with a B tree on the left and a B tree on the right. Okay, you provide this to Ristretto, and what it gives you back is a B tree object that has 3 functions on it, which are constructors. btree.empty gives you an empty tree. btree.leaf gives you a leaf node. btree.node takes 2 other nodes and gives you back a tree. So it's pretty easy to use. Once you've produced them, you can you can test whether they're empty nodes, leaf nodes, or other nodes. And then based on the as value, as left, as right, you have convenient data accesses as well. And it's all restricted by contract and checked as you do it so that you can't accidentally build a leaf with a string instead of an int. Does that make sense? Cool. Because then, of course, what you do is pattern matching, right? So you could, if you were trying to find the depth of a tree, you could do this procedurally. Or you could say, you know what, if a tree's empty, the depth is 0. If it's a leaf node, the depth is 1. And if it's a node with something on the left and something on the right, then it's the larger of the depth on the left and the depth on the right, plus 1. Okay, so this is one of the, in my opinion, this is one of the nicest features of functional languages, which procedural languages just don't give you. But it turns out you can do it at runtime if you really want to. Okay, I'm gonna hurry through this real-world example, so we can talk a little bit about how things work. So in this example, we're saying that we want to have buildings which we're eventually going to stick on a canvas. And we've decided that our buildings are going to be 4 ints, and those 4 ints are the x position, the y position, the width and the height. We've got a function here to add buildings. You give it your x and y position, your width and your height, and it just pushes it onto your list of buildings. And we've got a function to generate random buildings. You know, create a random number between 50 and 150, and another one the same for the width and the height. Scale your total width and your total height to make sure that you don't go off the edges, use random a couple more times, get your x and y, return the whole thing. And then we're just going to loop a few times and add random buildings. All right. Quick sanity check. This is what our buildings object looks like. Looks pretty good. We'll stick it on a canvas, get the canvas context, set the fill style, look through our buildings, and call fill rect. Right? Let's see a quick screenshot of what that looks like. What happened? Anyone see the bug out of interest? No? Well, that's good, I guess. What was that?
Go back.
Go back? Nah. I mean, you might see it if we go back. Let's go back. So here's our code. There's our building. There's random building. There's the code to stick stuff on a canvas. Anyone see the bug that time? Excellent. All right. Let's mark it up with Ristretto and see what we can find out. So here's our random building code. Random building doesn't take any inputs and returns a list of int. Cool. Our buildings are a list of lists of int. And our add building takes that list of int from random building and doesn't return anything. All right, let's run it and we'll see what happens. Oh yeah. So what we were doing is we were saying that this function takes an x, a y, a width and a height, but we were calling it with a list of x, y, width and height, right? And then JavaScript being, oh, you know what you're doing, I'm sure what you're doing is right, grabs that and sticks it in as the first argument as x, right? So you have a list where the first value is in a list, and then puts undefined, undefined, undefined as the other 3 values, right? And then you look at buildings, and building says, yeah, I'm a list of lists, and you go, right, that's cool. And actually, not quite this simple, but things slightly more complicated than this have literally taken me hours to track down in the real world, because you just don't see what you don't expect to see. Ristretto will pick it up for you. That function, it should only accept a single argument. Cool, okay, so we'll fix that. That's pretty easy to fix once we know it's there. And we'll run it again, and random building expected value of type int, but given clearly not an int. Well, of course, math.random doesn't return ints, it returns doubles. And, therefore, with height x and y not going to be ints, they're going to just be numbers. Okay, so this is actually important. Canvas does accept values which aren't int, but if you give it values which aren't int, it just does its best, so you'll get like blurry edges and stuff. So, it actually matters. I'll skip past this. There's a screenshot. Hooray, it worked. How does it work? Okay, so primitives. T passes primitives through. It can't really do anything meaningful with them except just check at invocation that the type is correct. So with primitives, you're kind of on your own. If you just say I assume this is an int. When you define the int for the first time, it'll check it, but it can't keep track of it after that. Right? And the output is completely unmodified. T wraps functions. The argument list length is checked on wrap, so it'll pick up things like we saw. Inputs are checked on invocation, so when you call the function, we'll check that the inputs are correct, and the result is checked on return. And actually, with a function, we peel it off in, argument by argument, and this is also how we support the partial application. So a function contract is usually a contract with a primitive on the left, and it returns a function on the right. With objects, T replaces the contents of the object. Each field type is checked, and field types are enforced forever using define setup. Okay, so what else could we do with this? We could add some kind of dependent types. Dependent types are really easy when you're doing it dynamically because you don't need to write a consistent type checker. Hooray. We could do integration with JavaScript engines. Now that you have all this lovely crunchy type information that people are expecting to be right, JavaScript engines can make use of that to make things go faster, which, as you recall, was one of the advantages of a static type system. And of course, you could use it to do some kind of static type checker tool as well if you wanted. Here's a bunch of links. There's a Ristretto homepage. There's a really good Ristretto users guide because Sam Lee, the intern, was awesome. This is me. Feel free to drop me an email if you want more information. Here's all the photo sources. And that's it. Are there any questions?
How slow is it?
Very good question. I haven't measured. Okay, so I actually have. I just started using it in anger on some toy code that I was writing. It doesn't look very expensive, maybe a 10% overhead. But it's going to depend on what you're doing, of course, yeah.
Most of what you're doing these checks at runtime.
Yep.
But your checks are static expressions. Can you do more interesting things like one of the values has to be an even number, or one of the values has to be greater than one of the other values? Absolutely,
you can. This is actually what dependent types will give you. But the answer is yes, you can. Not only can you do that, but somebody has already gone to the trouble of thinking about how you would express that as a type expression. So we can steal their work.
Why is it a type expression is what I'm saying? Why can't you just go x2 is greater than x1?
I mean, you could. Right. If you wanted to do it that way, you could. But the nice thing about type systems is that they tend to be pretty consistent and easy to read and easy to parse. Once you know the secrets, like you can read one anywhere and know what it's saying. So I'd be more inclined to use an existing dependent type system or something like it rather than just a bunch of ad hoc stuff.
You said a couple of times that this isn't really ready for people to use. Can you give any comment on if you tried to use it, what would be likely to happen? And what you think the sort of future is like in the near future for that?
Sure. Okay, so most likely what would happen is you would use it and you would get something completely random happening that you didn't expect and you'd give up. If you're a little bit more persistent, you'd dig into why something completely random was happening. Has anyone ever written code for a compiler that has bugs? Yeah. Okay, you know the experience you get where you're writing the code and you go, well, is this my bug? Is this the compiler's bug? What's going on here? Right? You'll get that same sort of thing. It won't be quite as nasty because you'll actually be able to, you've got a lot more access to inspect what's going on. But it's that sort of feeling that you'll get at the moment, right? Because we're not 100% convinced that everything is done right. If you're more persistent and that's the sort of thing that really floats your boat, then you'll dig into Ristretto and you'll make it better. And that'll be awesome, right? Because then somebody else can come along and use it as an actual production-ready system. The question was, are people working on improving it at the moment? The answer is me in my spare time sometimes, and I don't have much spare time.
I noticed that it's all kind of just regular JavaScript syntax, you're using basically regular functional programming in order to make it work. Have you thought about converting it into some kind of precompiled system using a macro, say like what Sweet.js does? Because there's some downsides to having the whole expression kind of locked away in a string, like I can't check that syntax easily before running my code, and I can't get highlighting on that easily and yeah, I mean, have you thought about actually kind of breaking that out and kind of mangling with the syntax a little bit and then kind of compiling it down to something that's valid.js?
That's a really good question because the answer is yes, we have. Ristretto is in two parts. The thing that parses those strings is not at all, interleaved with the thing that does the checks. So it's well and truly ready for somebody to come along and do something like an augmented version of contracts.coffee, or I didn't catch what it was that you mentioned.
Sweet.js, which is just like pre-compiled or macros for JavaScript.
Right. It would actually be pretty easy to hook Ristretto into one of those systems, right? Because rather than having to produce those strings, you just generate the object calls directly. We haven't done the work to do that though.
Have you looked into combining this with something like JS Compiler? I can think of, if you make JS Compiler aware of your type annotation, then you can combine that with this compile time type checking where possible.
Yes, we have. And actually, while that would work, an even better thing to do will be to take the JS Compiler type annotations and turn them into our type objects.
Or describe yours in the meta sort of structured comments that JS Compiler things typically use. So that the JS compiler could both check at runtime if possible or generate runtime checks.
Exactly. Yep, exactly. Yeah. I'm really interested in doing that at some stage. I just need to set aside a couple of months to do it.
Do we have any more questions? Over there.
Have you thought through maybe the dependent types to do something like what Perl does with the taint mode, because in the web world, like having a string that comes from the user, it comes with different contexts, and if you're going to print it out on the page, you have to escape it and so on. Is that something that the type system could help?
Absolutely, yeah. So we saw back here these type variables, and I said that these things were cryptographically locked away until you gave them to something which was able to unlock it, and you had to express in the type signature that this thing was able to unlock it. So you could definitely do something like that with tainted strings, right? You could lock them away, make sure that they could be passed around and put into objects and blah, 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 but they could only be unlocked by, possibly even just a single function. That'd be cool. We should do that.
One last question from anyone? Okay. Well, I'm sure you'd all like to join me in thanking Shane for an excellent talk about a very interesting new technology. Thank you very much. Okay, I believe we have the Penguin dinner next for those who are going to it. Otherwise, enjoy your evening.